Chemistry is awesome!
Alright, Assalamualaikum warahmatullahi wabarakatuh and Salam Sejahtera. So welcome back to this channel. In today's lesson, actually this is the second part of our lesson. If you guys miss out the first part of this lesson, it's okay. You can simply look for it in the playlist. Just look for the video how to perform stoichiometric calculations using mole concept part 1. This is the second part. So in this lesson I'm going to focus more on
purity of samples.
So what is purity of samples? Right, so purity of samples is defined as the percentage by mass or the mass percentage, or also we can use the mass composition, right? So of a specified substance in an impure sample. So I'll give you one example. So let's say we have a sample of sodium hydroxide. Sodium hydroxide. So normally the sample that we are using, in some cases the sample is not really 100% pure, and it might contains impurities, and that's why we need to determine actually how many or what is the percentage of the pure substance in the sample. So to calculate this, we are going to use this formula. So purity of samples is equals to the mass of pure substance divided by mass of impure sample, or the total mass of the sample, and we multiply with 100. So by if we use this equation, we can simply calculate the purity of samples. So remember just now I have said that let's say we have an impure sodium hydroxide sample. So we want to know in that impure sample of sodium hydroxide, so how many percent actually from the total sample or from the total mass of the impure sample is the mass of or the percentage of pure sodium hydroxide. So let's say we have I'm going to use one example here. So let's say the mass of the impure sodium hydroxide is 50 grams. It's 50 grams. So now we want to calculate the purity of sodium hydroxide in the sample. Right, so how to calculate this? So based on the given equation here, so mass of pure sodium hydroxide, so in this case let's just use this value. So let's say the mass of pure sodium hydroxide is 49.4 grams. So divide by 50 grams, which is the total mass of the impure sample of sodium hydroxide, right? And you multiply with 100 and we are going to get 98.8%. So what actually this 98.8% means to you? So how to read this percentage? So 98.8% here means the sample contains 98.8% of pure sodium hydroxide, while the remaining 1.2% is the percentage of what? Yes, percentage of
impurities.
Right, so now let's look at a few examples or a few exercises so that you get a clear understanding on this purity of samples.
So what do we have here? See, we have an impure sample of solid sodium carbonate. And what happened was, this impure sample of solid sodium carbonate is allowed to react with 0.1755 molar of hydrochloric acid solution. And this is the equation of the reaction. Okay, right. So let's say we have 0.233 gram sample of sodium carbonate requires 17.85 milliliters of hydrochloric acid solution. What is the purity of the sodium carbonate?
Okay, so to solve for this, so firstly, what we need to do is, right, so we need to calculate how many moles of hydrochloric acid used in the reaction. Okay, so we are going to use this formula, molarity times volume. Since the molarity was given together with the volume of acid, okay, also given in the question, so we just simply substitute these two values into this equation. Okay, so 0.1755 molar times 0.01785 liters, and we are going to get, okay, 3.13 times 10 to the power of negative 3 mole of, and remember, this is the amount of HCl reacted with, yes, reacted with sodium carbonate. Okay, so now let's get back to the equation. Okay, so now we are going to apply a stoichiometrical relationship here. Right, so let's look at the given equation. Okay, so from the equation, okay, one mole of sodium carbonate reacts with 2 moles of hydrochloric acid. Okay, or it can also be written as 2 moles of hydrochloric acid react with 1 mole of sodium carbonate. Okay, but we don't have hydrochloric acid, okay, in the quantity of 2 moles. So how many moles of hydrochloric acid actually reacted in the reaction? This is the amount of hydrochloric acid, okay, reacted with sodium carbonate. So therefore, if we have 3.13 times 10 to the power of negative 3 mole of hydrochloric acid, so this quantity of mole of hydrochloric acid should react with, okay, so you calculate this, we are going to get 1.57 times 10 to the power of negative 3 mole of sodium carbonate. Okay, so this is the mole of sodium carbonate reacted, and we knew that this sodium carbonate, okay, came from the impure sample of sodium carbonate. Okay, so right now we want to determine, okay, what is the percentage of sodium, this sodium carbonate, in its impure sample. Okay, right, so since we have already calculated just now the mole of sodium carbonate reacted, and this time we are going to determine what is the mass of sodium carbonate reacted. Okay, so this is the formula. Okay, we are going to use this formula or this equation. So mass of sodium carbonate equals to moles of sodium carbonate times molar mass of sodium carbonate. So mole of sodium carbonate 1.57 times 10 to the power negative 3 mole, so times with 106.01 grams per mole, which is the molar mass of sodium carbonate, and we are going to get 0.166 grams of sodium carbonate. Right, guys, so this is the mass of sodium carbonate. Okay, in order to determine the purity of sodium carbonate, so what we are going to do is mass of sodium carbonate divide by the mass of impure sample of sodium carbonate. Okay, and we are going to multiply with 100. Okay, since the mass of sodium carbonate is 0.166 grams and the mass of the sample is 0.2233 grams, okay, times 100, right? So we are going to get how many percent, guys? We are going to get 71.2% sodium carbonate. So this is the purity of sodium carbonate in the impure sample. So means that, okay, so out of 100% of the sample, only 71.2% is sodium carbonate, while the rest, or around 28.8%, okay, so that is the percentage of impurities.
Right guys, actually this question is the same question in your tutorial 1.3. Okay, tutorial 1.3, question number 2. Okay, question number 2. Okay, so you can look for this question in your tutorial book. Okay, right. So what do we have here? This time we have an impure sample of zinc weighing 50 grams. Okay, reacts with excess hydrochloric acid to produce 18 liters of hydrogen gas at room condition. Okay, and the question here is, firstly, write a balance equation for the reaction. Okay, and then calculate the mole of hydrogen gas produced, and lastly, determine the percentage of zinc in the impure sample.
So let's start with the first part of this question, A. Okay, so in A, what we need to do is we are going to balance this equation. So first we have zinc, right? So zinc reacts with hydrochloric acid. We are going to get zinc chloride and hydrogen gas. And remember guys, okay, so this equation is not balanced yet. So what should we do? Come on. Okay, so we are going to start with the most complex substance. Remember in the previous lesson, in the previous videos, okay, we have already discussed on how to balance chemical equation using inspection method. Okay, so we are going to start with the most complex substance. So in this case, zinc chloride is the most complex substance. Okay, so zinc, there is only 1 mole of zinc here, and that's why here also 1 mole of zinc. Okay, but Cl, okay, chlorine, in zinc chloride there are 2 moles of chlorine atoms. So since there are 2 moles of chlorine atoms in zinc chloride, so over here for this HCl we need to multiply, okay, by 2, right? So 2 moles of hydrochloric acid. So now let's check, let's do some inspection on both sides to make sure both sides of this equation is balanced. Okay, so on the left side here we have 1 mole of zinc, on the right side 1 mole of zinc. So we have 2 moles of chlorine, 2 moles of chlorine, and 2 moles of hydrogen, 2 moles of hydrogen. Okay, so the equation is balanced. Good job guys, good job. Alright, next, question B. Alright, so in B, we need to determine how many moles of hydrogen gas produced in this reaction. Okay, if you look at the question, stated in the question, so this reaction, okay, was done at room temperature. Okay, room temperature. So now we know that at room temperature, okay guys, at room temperature, if we have 1 mole of any gas, name it, any gas, if it is 1 mole, okay, so this 1 mole of gas occupies 24 liters. Okay, so don't confuse with at STP. Okay, so at STP, 1 mole of gas occupies 22.4 liters. Those are the for STP condition at STP. But in this question, this reaction occurred at room temperature. So that's why we are going to use this relationship here. Okay, 24 liters of hydrogen gas, okay, occupied by 1 mole of hydrogen gas. So therefore, if we have only 18 liters of hydrogen gas. So this means, okay, 18 liters of hydrogen gas occupied by, so this is how we calculate. Okay, so 18 liters of hydrogen gas times 1 mole of hydrogen gas divided by 24 liters of hydrogen gas. So liters of hydrogen gas cancel. So we are going to get 0.75 moles of hydrogen gas. Okay, so this is the mole of hydrogen gas produced in the reaction or released in the reaction. Right. Next, question C. Okay, in question C, we are going to use the balance equation from question A just now. Right, so from the balance equation, okay, so we knew that 1 mole of hydrogen gas produced from 1 mole of zinc. Okay, so this is a stoichiometrical relationship between hydrogen gas and zinc, right? However, in this reaction, okay, so the mole of hydrogen gas produced was 0.75 mole of hydrogen gas. So therefore, if we if the reaction produce 0.75 moles of hydrogen gas, so means that this 0.75 moles of hydrogen gas, okay, was produced from 0.75 mole of zinc. Okay, why? Because the ratio is 1 to 1. Okay, so we have equal number of moles, which is 0.75. Okay, so once we have calculated this, right? Okay, so we want to determine the mass, the mass of zinc reacted with this hydrochloric acid. Okay, so this is the molar mass of zinc, 65.4 grams per mole. Okay, by using this molar mass of zinc, okay, we know that from this molar mass of zinc, 1 mole of zinc weighs 65.4 grams. Okay, that if we have 1 mole of zinc. In this case, or in this reaction, we have how many moles? 0.75 mole of zinc. So therefore, 0.75 mole of zinc should weigh how many grams? Okay, so if we calculate this, we are going to get 49.05 grams, because this is less than 1 mole. See, if it is 1 mole, 65.4, but we have only 0.75, so that's why the mass is less than 65.4. It should be less than 65.4. Okay guys, so this is the mass, the mass of zinc reacted in the reaction. Okay, since we want to determine the purity of zinc in the sample, right? So this is just this is the mass of pure zinc in the impure sample of zinc. Okay, we have just calculated just now, right? And given in the question, right, the mass of impure sample of zinc is 50 grams. So therefore, if we want to determine the percentage of zinc in the impure sample of zinc, right, so how to calculate this? Okay, so mass of pure zinc divided by mass of impure sample, and we are going to times it with 100%. Okay, and substitute these two values into this equation. Okay, 49.05 grams over 50 grams times 100%, and finally we are going to get 98.1%. So this is the percentage of zinc, or we can say this is the purity of zinc in the impure sample of zinc. So means that the remaining 1.9% is the impurities. Yes, or the percentage of impurities.
Alright, we have come to the last and final question of the day. Okay, exercise 3. And actually, this question actually is the same question as question number 3 in your tutorial 1.3. Okay, so you guys can check in your tutorial book. Okay, it is the same question. Alright, so I'm not going to read this whole question. So let's convert this question, okay, from here to here. Okay, right, so what do we have in this question? We have a sample of iron ore. Okay, and the mass of this iron ore is 1.55 grams. Right, so for your information, guys, iron ore actually contains iron, not just iron, iron and impurities. Okay, impurities. So that's why if we want to extract this iron from this sample of iron ore, so this iron ore must be dissolved in an acid solution. Okay, so we are going to dissolve this iron ore into an acid solution. And what happened to this iron ore? So iron in the iron ore sample will be dissolved in this acid solution to produce iron 2 plus ion. Okay, or iron 2 ion. Okay, clear everybody? Right. And then in the next part of this question, okay, stated in the question, so this iron 2 solution later on is titrated, is titrated with potassium or with 0.02 molar potassium permanganate solution, KMnO4. Okay, and what happened in this titration? Okay, permanganate ion from the potassium permanganate is reduced to manganese 2 ion. Or we can say that this permanganate ion undergoes reduction. Okay, while iron 2, okay, iron 2 ion from this acid solution here, okay, is oxidized to form iron 3. Or we can simply say that iron 2 undergoes oxidation. And both of these reduction and oxidation occurred simultaneously. And that is why this reaction or this titration is also known as redox titration. Okay, redox titration. Right, and then in the last statement in this question tells us, okay, this titration requires 92.95 milliliters of potassium permanganate to reach equivalence point. Okay, what is equivalence point? Sounds familiar, right? Equivalence point. I know you have heard it somewhere before. Okay, so what is equivalence point? So equivalence point means the point in a titration at which the added titrant, what is the titrant here? Yes, the titrant is potassium permanganate, reacts completely with the analyte. So in this case, the analyte is iron 2 ion according to the stoichiometry. Okay, or in other words, we can say that equivalence point is the point at which both reactants reacted completely according to the stoichiometry. Okay, so it means that all of the reactants completely reacted. Right, so that is what we call as equivalence point. Equivalence point. Okay, and since this is a redox reaction, so that's why in the first part of this question A, we need to write down the balanced redox equation for this reaction. And in B, what we need to do is we need to determine, okay, what is the percentage of iron in this sample of iron ore.
Right, so let's start with the first part of this question. We need to write a balance equation for the titration. And since this reaction is a redox reaction, so we are going to do balancing redox equation using ion electron method. Remember in the last video, in the last lesson, okay, we have already discussed about this, right? Okay, so how to balance redox equation? So we were given the two half equation. The first half equation is permanganate, okay, is reduced to manganese 2, okay, reduction, and iron 2 is oxidized to iron 3. Okay, remember once we have separate this redox equation into two half equations, right, and the next step is we are going to balance the number of atoms other than oxygen and hydrogen. So in the first half equation, reduction equation here, reaction here. Okay, so on the left side there is 1 mole of manganese, the right side 1 mole of manganese, so the number of atoms of manganese on both sides, okay, are balanced, so no need to do anything, right? And then let's look at iron. So on the left side 1 mole of iron, on the right side also 1 mole of iron, so therefore the number of mole of iron atoms also balance on both sides, so no need to do anything. Okay, next we are going to balance atom oxygen, and also we are going to balance hydrogen atoms. Okay, so in this case in permanganate there are 4 moles of oxygen atoms here. Okay, 4 moles of oxygen atoms, so means that on the right side here we need to add 4 moles of water, and once we have added 4 moles of water, we have increased the number of mole of hydrogen from 0 to 8 moles of hydrogen. So we need to balance this 8 moles of hydrogen atoms by adding 8 moles of hydrogen ion on the left side. Okay, right, so in terms of atoms, okay, we are done for the first half equation, and then let's move to the second half equation. So for second half equation, or for this equation that involve these ions, or since there are no atoms other than iron, okay, so that's it, no need to do anything, right? And then we are going to balance the charges, okay, the charges. Okay, so for the first half equation, since we have 8 moles of H plus, means plus 8 the charge, and permanganate is minus 1, right? And manganese 2, okay, is plus 2, and water is 0. Okay, so if we total up the charges on the left side, we are going to get plus 7, while on the right side we are going to have plus 2. So it means that the charges are not balanced on both sides. Okay, so we need to add electrons. So how many electrons must be added, and which side should we add this electron? Yes, we are going to add electrons on the left side. So how many moles of electrons need to be added? Okay, good. So we need to add 5 moles of electrons. Okay, why 5 moles of electron? Because 5 mole of electrons carry negative 5. The charge is negative 5. So therefore negative 5 plus 8 plus minus 1, so we are going to get no longer plus 7, it should be plus 2. See, on the left side is plus 2, on the right side also plus 2. So it means that the charges on both sides of this first half equation is balanced. Alright, good. Okay, so let's move on to the second half equation. Right, so on the left side of this equation, okay, the charge is plus 2, and then on the right side also plus 3. Okay, so how to balance these different charges here? Okay, we are going to add electron on which side? Yes, on the right side. We are going to add 1 mole of electron. Okay, since 1 mole carries negative 1, the charge, and the total charge on the right side would be plus 2. So therefore, the charges on both sides are balanced. Okay, are balanced. Okay, so once we are done with balancing the charges, we are going to combine these two half equations to form the final equation, or to form the full redox equation. But the problem here is the number of electrons on both sides of both equations, okay, are different. Because if we want to combine these two half equations together, okay, the number of electrons on both half equations must be equalized. Why? Because these electrons must be cancelled at the end. Okay, because at the end we are going to cancel these electrons, so that's why, okay, the number of electrons must be equalized on in both half equations. So what should we do, guys? Yes, okay, so the second half equation here, so to equalize this number of electrons, since in the first half equation there are 5 moles of electrons, so that's why in the second half equation also we need to change this 1 electron into 5 moles of electron. And since we have multiply, okay, with 5, so the whole equation also must be, okay, times 5. Okay, so the half equation, the second half equation, okay, will look like this. Okay, right, and then we are going to combine these two half equations, right? So these 5 moles of electron cancel, 5 moles of electron cancel, and we are going to add up these two half equations, and finally this is our, okay, balance redox equation, right? Is this reaction in acidic or basic medium? How can we tell? Okay, actually this is in acidic medium or acidic solution. Remember in the question, okay, at the beginning of the question stated there, this sample of iron ore is dissolved in acidic solution. See, acidic solution, and that's why this reaction actually occurred in acidic medium. So we are going to stop here, so no need to add the last step. Okay, so this is the balance redox equation for this redox titration. Okay, for question B, okay, we need to calculate the percentage of iron in the sample of iron ore. Right, so in the question, given in the question, at equivalence point, okay, at equivalence point, potassium permanganate and iron 2 ion from the acid solution, okay, completely reacted. But at this moment, okay, we do not know yet how many moles actually of potassium permanganate reacted with this iron 2 ion. Okay, so that is what we are going to determine first. We are going to determine how many moles of potassium permanganate actually reacted at equivalence point. Okay, so at equivalence point, mole of potassium permanganate reacted, okay, is equals to molarity of potassium permanganate solution times volume of potassium permanganate. So volume here means volume of potassium permanganate needed to reach equivalence point. Okay, so if we substitute the values, okay, so 0.02 molar times 0.09295 liters, right? So we are going to get 0.001859 moles. So this is the mole of potassium permanganate reacted. And we know that in the redox reaction, permanganate ion from the potassium permanganate, okay, undergo reduction to produce manganese 2 plus. Okay, so since 1 mole of potassium permanganate contains 1 mole of permanganate, So therefore, if we have 0.001859 moles of potassium permanganate, it contains 0.001859 moles of permanganate. Okay, and from the balance equation, 1 mole of permanganate reacts with 5 moles of iron 2 ion. So therefore, if we have 0.001859 mole of permanganate, it should react with 0.009295 mole of iron 2. Okay, and remember this iron 2 ion actually came from iron in the iron ore. Remember iron ore, when we dissolve iron ore into the solution of acid or into this acid solution, so this iron in the iron ore dissolve to form iron 2. Remember? Okay, so that's why the moles of iron in iron ore and the moles of iron 2 in the solution, actually both of these, okay, same mole, same number of mole, which is 0.009295 mole. Alright. Okay, the mass of iron in iron ore is equals to moles of iron in iron ore times molar mass of iron. So if we solve for this, 0.009295 mole of iron in iron ore times its molar mass of iron, and we are going to get 0.5191 grams of iron in the iron ore. And then finally, okay, so we want to determine the percentage of iron in the 1.55 gram sample of iron ore, right? So mass of iron in iron ore divided by mass of iron ore times 100%. Okay, you substitute the values. Okay, 0.5191 grams divided by 1.55 grams times 100%, and finally we are going to get 33.49%. So this is the percentage of iron in the sample of iron ore. Right, that's all for now. Thank you for your time, okay, for watching this video. And in the next lesson, in part 3 of this lesson, we are going to discuss another two terms. Okay, another two terms. The first term is we are going to have a look at the limiting and the excess reactant. Okay, and lastly, we are going to discuss on percentage yield. Okay, percentage yield. Right. So those two in the next video, inshallah. Right, guys. Okay. So thank you once again. Bye bye.